Thanks. I'd like to thank the organizers for inviting me to speak here. It's been a wonderful workshop and a wonderful venue, and it's my first time in Florence. I'm really enjoying it. I'm going to talk about some past work, but also I've been revisiting some past work from a year ago, in motivated by some recent papers by Lionel and friends, and by Friedel, Pranzetti, and Reclario. So if you want to take a look at some of these recent advances in celestial holography, you should definitely check these out. And the basic context is going to be these infinite dimensional symmetry algebras that you discover in celestial holography by means of soft theorems. So Kamek, Mason, Rama, and Akshay. Okay. So there are multiple papers by the first three authors over the last few years, and this one was very recent. By now, you probably all have heard the basic spiel of celestial holography. The basic idea is that the symmetry group of flat space in 4 dimensions is SL2C, the Lorentz group. And that Lorentz group can alternatively be viewed as a symmetry group of the celestial sphere of Minkowski space, as a conformal group. So Strominger, Pastersky, Schauer, and other people, 10 years from now, tried to interpret this as saying that if there is holography in flat space, then the dual might most naturally live in a codimension 2 celestial sphere. So celestial holography says that for the flat space physics, for example, 4D scattering amplitudes of gauge theory of gravity should be accessible as correlation functions in a CCFT, in a celestial CFT that lives on the celestial sphere at null infinity. Now, in any holographic duality, the first thing one needs to do is to build a holographic dictionary that relates states in the bulk theory with operators in the boundary theory. There are two ways to do this. The first way is to relate states in the bulk to states in the bulk to operators in the boundary, and the other is to relate operators in the bulk to operators on the boundary. And the second way is called the extrapolate dictionary. And I'm deliberately not going to give any references for this because there will be people at MIT who get angry at me. But look at old papers by Daniel Harlow and friends. So the idea of the extrapolate dictionary also works in a bottom-up context, even if you don't have an explicit holographic dual. The idea is very simple. So just to illustrate it with flat space physics, if you have a momentum eigenstate e to the I k dot x, where the momentum k mu, k alpha alpha dot, depends on some frequency omega and some position on the celestial sphere z, then you can associate to this state a creation operator, A, of omega z z bar, A dagger. This creation operator you can take as a proxy for the dual operator. Why? Because if you have a scattering amplitude, then you can formally express it. You can express it through LSC reduction as a correlation function of a bunch of out operators and a bunch of in operators. And so that gives you like a proxy for a bottom-up holographic duality. Now, there's a version of this in ADS, which works much more precisely. And this is what's known as the extrapolate dictionary. In celestial holography, this was somewhat of a formal construction. It's somewhat obvious that these things are very naturally holographic. If you think that your holographic dual lives on a sphere, then these things are naturally labeled by positions on the sphere, z and z bar, and you can think of omega as some internal variable, or you can think of it as the Fourier conjugate of the u time variable on scry. So these creation operators are very tautologically holographic, but the question is, what can you do with it? Can you somehow use this holographic methodology, a way of thinking, to find better ways of computing any amplitudes? And it turns out that you can't do this on space-time, but Costello and Piquet found a very beautiful way in recent work to do it on twistor space. So the whole idea can be uplifted to twistor space in certain special theories called self-dual Yang-Mills and self-dual GR. All of these infinite dimensional soft symmetries can also be uplifted to twistor space. And on twistor space, there's a much more powerful extrapolate dictionary, and one gets a much more powerful operator product algebra of these extrapolate operators that you can use to bootstrap scattering amplitudes. So just to give you the rough idea, and then you can fall asleep if you want. Twistor space, if you turn your head, you can look at it, you can think of it as a strip cross R3. So up the strip goes a positive coordinate R positive, and this way, you can think of this direction as a two-sphere direction, as a CP1 direction. And you can think of R plus cross S3 as flat space, R4. And to each point in R4, it associates a CP1. Okay? What Costello and Piquet's idea was to build, so for each momentum eigenstate on space-time, you can associate a state in some theory on this six-dimensional space called twistor space. In that six-dimensional theory, you can do canonical coordination, and you can build the analog of creation and annihilation operators that very naturally live at this R going to infinity boundary, this boundary at infinity here. So this is a CP1, which you can say, we call it the CP1 at infinity or the line at infinity in twistor language. So there's an algebra of just bulk operators, these creation operators of states living at CP1 infinity. And the point is that this algebra is spanned by exactly the soft gluon states or the soft on states, depending on what theory you are. And there are certain amplitudes which are very close to being self-dual, like MHV amplitudes at tree level or all plus amplitudes at one loop level, which you can sort of bootstrap. So the operators that live at this boundary, these creation-like operators, satisfy some operator product algebra in the bulk sense. It happens to be very close to a two-dimensional CFT chiral OPE algebra. So it looks like the product of two operators will look like 1 over Z1 minus Z2 times another operator. And this is going to be signature agnostic. So in amplitudes, we usually analytically continue to complex momenta. And here I'm just describing it in terms of Euclidean signature, but I'm shortly going to just complexify space-time. Yeah, so I'll use the Lorentzian signature scry to build asymptotic symmetry charges shortly. Here I'm just because twistor space itself is the same. This is just a picture, but when I come to CP3, I'll sort of describe exactly where the line at infinity is and how the charges are built in terms of scry. So Costello and Piquet, I forgot to check the year. This is probably 22, right? You remember? Yeah. So in their first paper from 22, which is called Celestial Holography Meets Twisted Holography, Costello and Piquet use a trick. Instead of, so the algebra of operators living here is an infinite dimensional symmetry algebra, which you can use to bootstrap amplitudes. That's why this is interesting. But how do you compute this algebra? Instead of actually finding a basis of creation operators that live at infinity, they use a trick. They use a trick that the algebra of local gauge invariant operators at CP1 infinity is actually isomorphic to something called the Kosul dual of the algebra of operators living on CP1 at the origin. So here's a CP1 at the origin. Their idea was to formally compute this through some mathematical technique called Kosul duality, which is very close to the idea of placing a brane, like a formal brane at the origin, a D1 brane wrapping the CP1, and then trying to figure out what is the operator algebra that might live. Basically, how the operators on the brane might couple to the operators in the bulk. But this is a bit of a formal construction. What I wanted to understand was if we could actually write down a basis of operators directly on CP1 infinity and then directly try to compute their algebra, but also try to connect it to other definitions of the charge aspects for these soft symmetries that have appeared in the literature, in particular in these papers mentioned above. So regardless, Costello and Paquette have made great use of just an abstract algebra that they find using this Kosul duality approach, and they've been able to compute things like two-loop all-plus amplitudes in certain non-supersymmetric QCD theories, as long as they manage to make the algebra anomaly-free by adding some flavor content. So it actually has some applications. You would be surprised to know that celestial holography is finding some applications after all. But I'm not going to talk about it. Roland will actually talk about it. So my talk is more like an appetizer for Roland's talk. But in any case, let me talk about some of the geometry of twistor space to begin with. Okay, so Sonia already mentioned this. So let me go over this slightly quickly. Twistor space of flat space is just complex projective 3 space. And flat space itself can be recovered, so complexified, compactified flat space can be recovered as the space of CP1s that are linearly embedded in this CP3. You're all probably familiar with the space of C2s linearly embedded in C4. This happens to be an isomorphic problem. And space of lines in PT gives you a copy of Grassmannian 2 in C4. And GR24 is four complex dimensional. Is everyone familiar with the Grassmannian? You've probably seen this in a million NEMA talks by now. So this is 4 complex dimensional, and it has a subset C4, which you can identify as complexified Minkowski space. So that's the geometric idea of twistor theory. If I give a homogeneous coordinate Zi in CP3, then a linearly embedded line just looks like Zi equals x alpha I sigma alpha, where sigma alpha is a parameter on an auxiliary CP1. So these are parametrized lines, and x alpha I are some 2x4 matrices, alpha, beta, gamma, delta, A, B, C, D, taken up to GL to C rotations from the left. Okay, in pictures, if you have space-time C4 here, then each point in space-time is given by an entry x alpha I. And twistor space is somewhat like a tube in that each point corresponds to a linearly embedded CP1 associated to that point. Now, we'll focus on a specific class of such lines. There are 3 main classes of lines that are of interest. The first are the lines that are in the interior of the compactified geometry, so lines for points corresponding to points in C4. These would be familiar. So if you pick your favorite coordinate patch of the Grassmannian, you can take it to be 1, 0, 0, 1, And this 2 by 2 matrix, you take it to be x alpha alpha dot. And if you plug it in there, you can eliminate sigma alpha, and you get the line CP1x being just mu alpha dot equals x alpha alpha dot lambda alpha. So this is the C4 coordinate patch. Null infinity is everything that's not in this coordinate patch. So points on null infinity will correspond to matrices where the first two columns form a non-invertible matrix. So you can't bring it to the standard 1001 form. So take it to be a 2 by 2 matrix. Let me call it Q. And then the identity matrix in any other pair of columns. I'm going to take it to be the second pair of columns. This Q is going to be determinant 0 because it has to be non-invertible. So it corresponds to a null vector, Q alpha alpha dot, which I can decompose in terms of a pair of spinors. And this is complexified, so these are not necessarily complex conjugates of each other. When they are complex conjugates of each other, you get a point on Lorentzian null infinity. And so the picture is something like the usual. It's not exactly like that, but you can think of it as there's a single point at infinity that I'll come to. There's a null infinity, and there are points here. These points, so you can think of null infinity as a light cone of spatial infinity. And then along this light cone are null vectors that go like this. And this Q alpha alpha dot just describes this null vector. So it describes 3 degrees of freedom, which are the Bondi time, the length of the null vector, and the angular position, which you could take to be zeta 2 over zeta 1, if you like. Okay. Any questions about the geometry? So for these kind of points, you can derive the twistor lines. The twistor lines just become lambda alpha equals Q alpha alpha dot mu alpha dot. And that's where your charge aspects would usually be defined. There's Roman. Oh, you're at the back. That's where your charge aspects would usually be defined. And that's where this Bramson-Todd integral formula that you used works. For each line in twistor space, there corresponds a Penrose integral formula. And for lines like that, you get the Bramson-Todd formula, to my understanding. Anyway, spatial infinity I naught. So in this compactified geometry, there's only one point at infinity. I plus I minus and I naught get identified into each other. But it's very convenient for just flat space physics, so we're going to go with that. This doesn't work for Schwarzschild, but it works in flat space. So the point at spatial infinity is the obvious point where this 2 by 2 matrix Q is identically 0. So that's a single point, and it's outside the interior C4. So this gives you I naught. And the line corresponding to I naught is just you plug in this matrix into that equation, and you literally get lambda alpha equals 0, and mu alpha dot is not 0, just because lambda and mu. Sorry, I forgot to say, thankfully Sonia already said this. I was decomposing Zi as lambda alpha mu alpha dot. So when you plug that line in, you get lambda alpha equals 0 because the first two columns of this gives you lambda alpha equals 0. And the second entry just gives you mu1 is sigma 1 and mu2 is sigma 2. So you just get this simple straight line. And this is the line at the top that I had drawn there, CP1 infinity. Yeah, I just haven't thought about it. This is the complex, yeah, those things are not in the compactification of real Minkowski space. So I'm not sure what interpretation there would be. There are points on some kind of, so scry itself, I only wrote one patch of scry where the last two columns are invertible. There's probably like a compactification of that. Yeah, in this diagram, scry is non-compact. I just drew the Penrose diagram, but there's a compactification where scry is not affine anymore. And I think that would be the interpretation, just points at infinity on scry itself. I haven't checked at this point, there's only a unique inode. In the real case, there's a unique inode, that I'm sure of. Okay. This is interesting because the first question that we want to ask is, where do these charges that I'm going to talk about, where are these creation operators going to live? So these creation operators are going to live near the line at infinity. We want to do holography, so we want to construct a boundary in our space. What is the natural boundary in twistor space? The natural boundary in twistor space is that line at infinity that I just rubbed off, this line, because it corresponds to the point at spatial infinity. But twistor space is 6-dimensional, while this line is 2-dimensional. In complex geometry, the natural notion of a boundary would have been a boundary divisor, which would have been complex codimension 1. Just like in real geometry, a boundary is a real codimension 1 geometry. In this case, in complex geometry, the natural notion would be a complex codimension 1 thing. I'm now working in CP3, so complex geometry of that, I'd say. 6 real dimensional. I was using, I was mixing up, yeah. So twisted space is 3 complex dimensional. And I want to construct a boundary divisor which is complex codimension 1. And the natural boundary divisor is nowhere to be found because this line is complex codimension 2. The resolution came up in my work with Costello and Paquette on this Burns holography story. The resolution was very simple. We actually didn't write it up for the case of PT. So let me now try to write it up. You take Li naught, and you basically blow up PT along Li naught. So let me just draw in pictures what this looks like. If you think of PT, so earlier I drew a picture of PT as a strip, but a more accurate picture is something like this. It basically looks like a fibration over CP1 cross CP1. You have a pair of coordinates mu and lambda. In the regions where neither mu nor lambda is 0, you can project twistor space onto CP1 with homogeneous coordinates mu times CP1 with homogeneous coordinates lambda. So these lines here are copies of CP1 cross CP1. But this fails exactly when lambda alpha is 0 or when mu alpha dot is 0. So these points are just CP1 lambda and CP1 mu. So through the bulk of this geometry, both CP1s have non-vanishing size, but at the tips of this geometry, either CP1 mu shrinks or CP1 lambda shrinks. Since this is the line at infinity, CP1 infinity, what I want to do is I want to blow up this line and create a codimension 1 divisor. That in pictures just this. This one is undeformed, but I replace that point by the line that's described by the angles of approach. So this now becomes CP1 mu times CP1 lambda. So there's a more geometric way of defining the blow-up, but in the interest of time, let me not tell you. But that's the basic picture. This is now a complex codimension 1 geometry. And the celestial CFT, which will be a 2-dimensional conformal field theory, will live on this CP1 that gets created by the blow-up. It's basically at any finite point in twistor space, it would have lived on this CP1, and this CP1 at infinity that got created by the blow-up is just the limit as you approach CP1 mu, is the limit of all these CP1 lambdas. So that's where celestial CFT is going to live, and my charges for all my soft gluon symmetries are going to live on that divisor that I created. So how do I express these charges? This was just kinematics. Now I have to actually come to a dynamical theory. So I'm going to take the example of self-dual Yang-Mills theory. Self-dual Yang-Mills theory is very simple. It's an integrable subsector of Yang-Mills theory whose only amplitudes are the all plus amplitudes familiar from QCD, all plus one loop amplitudes, and the tree level MHV bar amplitude. It has a simple action as well. It's just B wedge F, where F is the curvature of some gauge field. And here I'm going to work with a Euclidean real slice because I want to work in terms of actions. But at the level of equations of motion, you can work on the complexified Minkowski space. Here, this is Euclidean R4. This is the curvature of some gauge connection I'm taking on R4. And instead of working with the Yang-Mills action, I've taken a different action. B is a generic two-form field, but it satisfies an anti-self duality condition. So it's a Lagrange multiplier field. And the equation of motion of B tells you that F has to be a self-dual field. So this is a Lagrange multiplier and just imposes self-duality as an equation of motion. There's no other way to get an action for self-dual theories that's Lorentz invariant. This can be uplifted to a holomorphic theory on PT. So strictly speaking, I'm going to work on a slightly smaller geometry, PT prime, which is going to be PT minus the line at infinity. This geometry is diffeomorphic to R4 cross CP1. You can identify this R4 as your flat space, and you can write down a 6-dimensional theory that lives on R4 cross CP1, whose KK reduction along CP1 gives you back this action. So that's the idea. So there's a theory on PT prime. There's a volume form on PT prime, which is the familiar object that you probably use in positive geometry. Z, dz, 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 the volume form on complex projective 3 space. Wedged against, I forgot a trace, but just imagine there's a trace there. There's a field curly B, which will be the analog of B. And there's a curvature, curly F, which will be the analog of F. So on PT prime, there'll be a connection, curly A, which will be a Lie algebra valued anti-holomorphic differential form, AI bar dz bar I bar. This will have an anti-holomorphic field strength, d bar A plus A wedge A. And this theory, and curly B is a Lagrange multiplier with an appropriate homogeneity for the action to make sense. The equation of motion of this theory just tells you that curly F is 0, so curly A is a holomorphically flat connection. And there's a famous theorem of Ward that tells you that if you have the data of such a flat connection on PT prime, then you can and some reality conditions if you like, then you can construct a solution of the self-dual Yang-Mills equation, this thing. So at the level of equations of motion, this correspondence works for the whole complexified geometry. But it's useful to work in terms of actions because we want to write charges for soft symmetries and that kind of thing. I don't remember when I started. Do I have 15 minutes? Okay. Good. Now, any questions about the setup? The idea is that this 6-dimensional theory on R4 cross CP1, when you KK reduce it at the level of the action, you literally get that B wedge F action on R4. Okay? All the twisted theorists are wrinkling their nose, but I hope nobody kills me after the talk. That's why I gave you chocolates. Okay, anyway, so this is the theory that we want to study holographically, bottom up. The first step in the procedure is to uplift this theory from PT prime to this blow-up geometry. Let me call that blow-up geometry PT bar, because I don't want to keep writing blow-up of PT along this. I wrote L. That L was CP1 line. So let PT bar be the blow-up along CP1 I naught of PT. So all I've done is I've taken PT, replaced this line to create PT prime, but added back that humongous CP1 cross CP1. Now, I want to uplift that action to PT bar. So how do I do this? To uplift this action to a space with boundary, I need to describe boundary conditions at the boundary divisor. So what boundary conditions do we choose? As any good Carolian physicist would tell you, the choice of boundary condition is more of an art than a science. We'll choose the most relaxed boundary conditions that we can. But definitely, we want the action to make sense if I just naively extend it. In particular, we want the interaction term to make sense. The interaction term takes this form. And I want the interaction term, I want the fields to die off at the boundary at a well enough rate such that this interaction term doesn't blow up at infinity. Because I'm going to use this interaction term to compute amplitudes, and I don't want my amplitudes to blow up. This analysis is easier done in affine coordinates instead of homogeneous coordinates. So let me translate to affine coordinates on CP3. So introduce a pair of affine coordinates v alpha dot, which are mu alpha dot over lambda naught, and work in the patch where lambda naught is not 0, and z equals lambda 1 over lambda naught. Now, what is the blow up? The blow ups, except the extra divisor that I created in the blow up, lives at lambda naught equals infinity. So in these coordinates, the boundary lies at v alpha dot going to infinity. And the fact that I've blown the geometry up just means that I'm taking the limit as both lambda 1 and lambda naught go to infinity, but by keeping the ratio fixed. So I take the limit, lambda naught goes to 0. Sorry, I said infinity. I'm taking the limit lambda naught goes to 0, lambda 1 goes to 0, while keeping z fixed. And b alpha dot goes to infinity. This limit can be made more explicit by a further change of coordinates. The further change of coordinates is to define, basically you define a ratio v1 over v2, and you just keep that fixed, and you use v1, you set v1 equals 1 over some new coordinate n, such that v1 goes to infinity corresponds to n going to 0. So this limit, n going to 0 means, v alpha dot going to infinity. And the ratios of v1 is fixed, so that tells you what's the angle of approach towards infinity along CP1 mu. And z tells you the angle of approach to infinity along CP1 lambda. So n is the coordinate normal to the boundary. And giving a boundary condition just means telling you how the fields behave at n equals 0. Okay, so the volume form d cubed z in holomorphic in these affine coordinates is just dz wedge dv1 wedge dv2. When you plug in v1 equals 1 over n and v2 equals y over n, you get dz wedge dy which dn or n cubed. So this volume form has a third order pole at the divisor at infinity. You have the interaction term, which is a cubic interaction. What is the most natural boundary condition? How should B and A fall off as n goes to 0 so that the product of d cubed z wedge, that cubic term, is regular? Just going to say that A goes like order n, and B also goes like order n. So both A and B, this is the most relaxed boundary condition, both A and B go as order n as n approaches 0. Okay? With this boundary condition, now you can construct operators living at the boundary. For that, we need the notion of, oh, I can use that board. For that, we need the notion of states. The idea will be that first I'll find a basis of states, and for each state, I'll construct an operator. And I'll show you that magically that operator will localize on the boundary if I have enough time. Probably don't have enough time. Okay, let me go quickly. Soft gluons on twistor space, soft gluons are represented by solutions of the linearized field equation of that action. The linearized field equation is just d bar A equals d bar B equals 0. Soft positive holistic gluons are those states with B equals 0. Soft negative holistic gluons are those states with A equals 0. So let's start with soft positive holistic gluons. These are solved by, this has a basis of solutions, A, K, L, M, which looks like V1 dot to the K. I'm writing it in affine coordinates because it's just easier. And then these are all not one forms. So I have to give you a not one form. The easiest way is to give you the d bar of a singular not one form. So this is going to be a distributional wave function for these soft gluon states. C to the, what convention do you have? Oh, it doesn't matter really. Minus K minus L plus M. Okay? This gives you a basis. Now, these states are non-normalizable states, which are the states of interest in holography. A normalizable state would have been a state which satisfies that boundary condition. These states are soft gluon states. There's something called the Penrose transform, which you can use to literally translate these. The KK reduction procedure I was mentioning, you can use that to translate these to space-time wave functions, and you get exactly positive LST soft gluon wave functions. But these, quite importantly, violate the boundary condition. So V alpha dot was 1 comma y over n. So this state violates the boundary condition to order k plus L. If you just plug in this product V1 and V2, y to the L d bar of that power of z. Because it violates the boundary condition, it's like your familiar Witten diagram type external state. The Witten in ADS-CFT, your external states are delta function norm. Your states violate the boundary condition, but by only a delta function amount at the boundary of ADS. This here, these here are soft states, and they violate the boundary condition at z equals 0 or z equals infinity to some amount. There's also a notion of positive and negative frequency. States which contain positive powers of z here are positive frequency. States which contain negative powers of z are negative frequency, but let me not dwell on that. Okay. Now that I have the states, I can construct the operators associated with these states. So the inner product between two asymptotic states can be computed by picking a Cauchy surface. This is a 6 real dimensional geometry. You have to pick a 5-dimensional Cauchy surface. The geometry, there's another picture of twistor space where you express it as the total space of O1 plus O1 over CP1. This is a picture of PT prime, twistor space with the boundary removed. Here, the idea to pick a Cauchy surface is to mimic what you do in a 2D CFT. Now, what do you do on a 2D CFT? Your Cauchy surface in the 2D CFT is a circle on the sphere. So pick a circle on the sphere. This sphere has coordinates z, so this circle can be mod z equals 1. And then just pick the fiber over all the points on the circle. So the coordinates in the fiber direction are v alpha dots, v1 here, v2 here. So this 5-dimensional surface is going to be your Cauchy surface. And this was first discovered by Sabrina Pistersky, not in twisted space, but in flat space. Cool. I'll just construct the charges. I'm just getting to it, and then I'll finish. But yeah, this idea first came to Sabrina in flat space and to Kevin and Davide in their older work on twisted holography. And I realized that the idea is just the same. I can just use it together and write a paper. So here we go. You use this Cauchy surface. So you have your volume form dz, d2v, and then delta A wedge delta B. All right, what do? To construct charges corresponding to these states, you have to construct creation operators corresponding to these states. The idea is to just plug that state in here. So these are some linearized solutions for A. You plug that in here, and you construct the following charges. J, K, L, subscript M. M will correspond to a mode number. So you have a contour integral in Z, an integral over d2v above these z's on this contour. A, the states that I wrote here, A, K, L, M, wedge delta B. Okay. To construct the charges, there's some subtlety that Lionel and friends discuss in their paper. I don't remember who pointed it out first. Just the fact that you have to remove this delta from B means that you can get some boundary terms in configuration space. I'm not going to dwell on that too much. I haven't really figured that out yet. But these are the charges that you get. You plug the states in here, and here's where the magic happens. The state is n to the minus k minus L. Oh, sorry. Yeah, now you also plug in that expression for the volume form. So that's dy dn over n cubed. So even before you start, you have a third order pole. Then you have a further pole, which goes like n to the 3 plus k plus L. Y to the L d bar z to the, where is it? Z to some power B. Now you can integrate this d bar by parts and pick up the pole in n. When you pick up the pole in n is at n equals 0. So your state localizes at n equals 0. So this is a contour integral that surrounds the point z equals 0 with a pole of order k plus L plus m. And then you get, when you integrate the d bar by parts, dn over n to the 3 plus k plus L, and then a completely regular integral over mu. This is your quadratic Q, Lionel. This is CP1 mu. This is where the Bramson-Tord integral formula breathes. Power B. Okay, this is the expression for the charge. At this stage, you can assume that curly B is metamorphic in n. You can expand in n, and this contour integral at n equals 0 can be done as if it was a derivative in n acting on B. But let me not write that. I also want to talk about how to make this gauge invariant. But in the interest of time, I'll just do that at some later point. Let me just, any questions about this construction before I conclude? Yeah, so this curly B as an operator will satisfy the appropriate boundary condition. If this wasn't there, then this charge would just vanish at n equals 0. Sorry, I forgot to say this expression. Right, this expression is evaluated at n equals 0. Let me write one more expression. Lunch is in 15 minutes, right? Let me write one more expression. So you can now write a current. The contour integral over m is just a mode integral. So you can instead define a current, which is now depends locally on z, but is integrated over the CP1 mu, on which y is now a coordinate. Y, I remind you, was v1 over v2 or something. So jkl of z is dy y to the L, the k plus L plus 2th derivative of b evaluated at n equals 0, and y is integrated over CP1. All right? B as an operator, I'm going to assume has the boundary condition that I require. So B vanishes to first order. So if these derivatives weren't there, then this would have been a triviality. I'm evaluating it at n equals 0, and B vanishes to first order at n equals 0. But because of the derivatives, even for k equals L equals 0, even for the leading soft gluon, there are two derivatives, so there's a non-trivial charge that survives. But this is just linear theory. You have to dress the B by some frames that live on that line, and that makes it gauge invariant. Oh, one question that I got, one more expression. One question that I got was how to define the other helicity charges, and that's very easy in this formalism. This was a cute application I found. It's just this expression. So that defines the charges in the other helicity, and I'll try to think about how to write it in terms of Friedel, Pranzetti, Raclario, but that's a question for another talk. Okay, let me just finish now. I've taken enough time. Thanks.
Questions? So have you tried to translate your expression on space-time?
Yeah, I'll just tell you later. Didn't have time. That's like 10 minutes down the notes I wrote.
Okay. And so this should be interpreted as the charges at space-like infinity?
At u equals minus infinity in the real language, yeah. It's scribe plus minus, yeah.
Do we have any other questions? I've actually got one. So at the very beginning, you mentioned that this type of dictionary doesn't exist for space-time. That it only worked in twistor space.
To my understanding, yes.
But you said it like it just doesn't exist in space-time. Was there a block? Is there something that?
Okay, maybe the better thing to say is the dictionary exists in the sense that people just take the state and map it to the creation operator. Sure. It's just not useful.
It's not useful?
Yeah, it exists in that linear theory sense.
Okay.
I was wrong. Of course, I even described it. But it's just, it becomes useful when you carry it over to twistors. Oh, sorry, I think what I meant was, you know how in ADS, boundary time is the same as bulk time, right? Boundary Cauchy surfaces are the same as bulk Cauchy surfaces. In Minkowski space, I wrote down a formal dictionary, state goes to creation operator, but that doesn't make sense because my Cauchy surfaces are in the bulk don't intersect the boundary celestial sphere in a sphere Cauchy surface, which would be in a circle. So these operators couldn't be interpreted as operators describing states in a 2D CFT Hilbert space. That was the problem that was on my mind. Here, and Sabrina Sabrina in her beautiful paper just tried to take surfaces that intersect the celestial sphere on circles. They're not Cauchy surfaces, but she also gets similar charges. Now, the question was, in that space-time case, she just made a choice. Is it a good quantization or not if I just choose a random surface instead of a constant time surface? But here, the choice of these spaces as Cauchy surfaces, it was very natural. It was literally motivated from that strip picture that I had drawn for you earlier. That was very similar to ADS holography. So that's why here the Cauchy surface is very natural. It's very close to what you do in ADS with a two-sphere boundary, and that's why I think this is a better way to think about these things. A more precise way to think about these things.
I've got one more question then. So just motivation-wise?
Yeah.
So I remember Daniel and Douglas playing all sorts of games with this in ADS, right? The extrapolate dictionary. Is that the aspiration is for similar So yeah, what do you see? What do you see coming from that when it's like fully realized
Right.
in flat space-time? What can we do that we?
So once we, no, my aspiration is more to compute amplitudes.
Okay.
So here, these operators, once I have these explicit expressions on twistor space, I can compute the operator products of these operators. And these operator products in good situations at the quantum level as well are they resemble 2D CFT operator products. Even if there isn't actually a 2D CFT, the OPEs of these integrated non-local operators in the bulk represent 2D CFT OPEs. And this can be used to reproduce certain rational amplitudes. So amplitudes that don't have any transcendental dependence, but only go like whenever Zij, Zkl, things like that, like the all plus amplitudes at one loop, things like that. That's the ultimate aim. So Kevin already succeeded in doing that slightly formally. He didn't construct explicit operators. He just constructed the OP using this mathematical technique of causal duality, which is going to give you the correct answer. But it works in the Yang-Mills case. We don't know how to make it work in the gravity case. We don't know how to use it in the gravity case to compute amplitudes. One of the hopes is I do this here first, I do it in the gravity case, and then since I have explicit operators, I can just compute their correlation functions and define some amplitudes in gravity as well. So,
So your N there is like just the, on the more space-time based formulae that we had, it's like the R, I suppose, and the radius going out to infinity. And of course, we had a similar thing where formally stuff is blowing up as R goes to infinity, or your N is tending towards 0. And
that N is going to be like U, I guess.
I was thinking it's more like R.
No, it's going to be like U.
Ah, okay.
Or
sorry, about what I was about to say then probably makes no sense.
You might be right. I'll discuss with you. It's like a quarter transformation.
N is like 1 over R,
Maybe.
and so we had this thing of having something that's divergent, but then we regulated it by
this N is like your
taking the
Q.
residue.
This N is like your Q. Is Q more like R?
No,
Sorry.
No. Your Y is RQ. Oh, sorry. Maybe we better do this later. Let everyone go to lunch. I'm sorry. Yeah.
David, do you have a question?
It's not so much a question as a comment, which is just that I think a lot of the things you're doing are very similar to stuff that Wei and Sean did in their papers, in particular constructing these charges out of boundary values of the twistor fields themselves. I think you've done a much cleaner job than they did. But a lot of the ideas, in particular using the near fibration of twistor space over P1 cross P1, etc., is stuff that they were using.
Yeah, but this stuff already appeared in our Burn space paper for the Burn space twistor space context. I was just trying to do it for the flat space case. But I'll make sure to cite them, of course. They're all friends. Yeah. We're all friends, yeah.
Awesome. Let's for a great talk.
Thank you.